can generalize. And so the scaling here is really over tasks, over many different objects, over many different environments. And as we all know, or those of you who have worked with a real robot or tried to train a real robot know that it's really, really difficult to do that on a real robot, or pretty annoying. And so there's a lot of work on simulation, but then you have the problem of the sim to real gap and so on. So we've been in my lab looking at very many different ways on how to maybe scale robot learning. And so one particular area, and I'm just realizing I don't have my glasses on. I can't. It's like I can't see. 1 second. Okay. So one particular way we worked on in the lab on trying to scale robot learning is by using basically priors or structural priors, algorithms, physics models, simulators, renderers, and basically make the underlying physical process of these basically algorithms, if you want, or models differentiable, and plug them in and together with the learning method to maybe learn certain parts of a perception pipeline in particular online. We also more recently look more and more at differentiable simulators, specifically for deformable objects. So all of these are ways to include structure and priors in the learning method in order to reduce the search space and hopefully reduce requirements for training. And we've also done quite a bit of work on imitation learning or learning from demonstrations, which is very useful to bootstrap learning as well. We looked a lot at multimodality, so not just using vision, but also depth, motion, language even, or of course the sense of touch, and more recently also sound. Because the more information you have, often it gets easier to actually distinguish or just separate certain signals from others and do better estimation. And then we also looked at including symbolic reasoning and different layers of abstraction into a learning pipeline, again, to reduce the amount of training data you actually need on a real robot. And so I had a somewhat hard time to pick one of these areas. And so I decided to go with this particular area because we also have some work that we actually just presented at ICRA, and I see Toki joined, which is great because they're going to present his work. He's sitting there at the very back, Toki wave. So if you want to get all the detailed information that goes beyond what I can present today, then you should totally talk to Toki. Okay, so one of the things we're really interested in my lab, and in particular Toki is working on, is really long horizon planning. And ultimately, it would be wonderful if our research in the lab enables robots to perform long horizon planning, where the robot is given a high-level goal, such as cooking a meal. And then, of course, what that means is that the robot needs to figure out a sequence of action to achieve this goal. And planning every joint motor command to accomplish such a long horizon task isn't computationally feasible. So it's helpful to abstract away details of the environment, such as the exact poses or mesh geometries of the objects, and operate at the level of the symbols, for example, on whether this pot is on the stove or this microwave is closed. And using symbols to plan over long horizons is called task planning, and it has its root actually in early AI, when researchers studied how to give robots the ability to reason about symbols and through symbols. Okay, so task planning, however, as I'm sure many of you know, is not really enough to have robots perform tasks in real world. So consider this example, where the robot needs to transfer this mug from the dishwasher into the cabinet. And task planning might come up with a simple two-step solution to this problem, where first the robot picks up the mug and second places the mug in the cabinet. But if the robot blindly executes these two-step actions, it might not actually succeed. So in this case, you see it grabs the mug from the bottom, which was the easiest thing to do from the dishwasher. But then it's not easy to actually place that mug into the cup without colliding with that actual shelf, right? we purposefully extracted away the environment with symbols so that we can operate with on these symbols with task planning. But then ultimately we can't ignore these geometric details if we actually want to execute the task plan in the real world. Okay, so this motivates the need for motion planning, where we can plan a motion trajectory that will actually successfully execute the sequence of action proposed by the task planner. But in some cases, the motion planner might not actually be able to find a feasible trajectory for the given sequence of actions. So, for example, after picking the mug, the robot might need to place the mug on the counter first so that it picks it up from a different configuration and then place it upright in the cabinet. So this task plan, now this alternative one, has 4 different actions and is different from the task plan with the original 2 steps. This means that motion planning can actually affect the task plan, and we need to incorporate feedback from this motion planner back to the task planner so that we can come up with a task plan that is both symbolically correct and geometrically feasible. And what is this called? This integrated loop is called task and motion planning. And there's, of course, a lot of work out there. And I just picked 2 here. It has certainly seen a huge growth of interest. And these are videos from 2 state-of-the-art algorithms, TAMP algorithm, which can perform long horizon tasks, such as grabbing an object outside the robot's workspace, using a hook to bring it closer, performing food preparation tasks in the kitchen. So TAMP can actually find these impressive solutions to these long horizon problems, but the catch is that it's extremely computationally expensive. So in these, to generate the solutions in these videos, it actually takes several minutes to solve. And as a result, previous TAMP methods are often working in simulated environments or pretty highly controlled environments where there are no moving objects or external disturbances. So we asked, or basically Toki started to look at this problem and wondered, like, how can we do task and motion planning in the real world where these disturbances and moving objects actually exist? Because we can't really expect the real world to just pause for several minutes before the robot has finished computing the plan. Okay, so basically what I'm going to talk about is, okay, once we have task and motion planning, we really want to connect it to the real world, and I'm going to talk a little bit about this work on object-centric TAMP, not too deeply, but just to give you an idea of what we can do with this particular work. So again, the focus here is to apply task and motion planning in the real world that is dynamic as well. So here's again this problem with the hook, where the robot needs to manipulate this object outside of its workspace. So there are 4 objects, a table, a large box, a small box, and an L-shaped hook. And now maybe we ask this robot to place the small box on this large box, but the small box is outside of the workspace. And so task planning uses symbolic reasoning to come up with a sequence of action to accomplish this goal. So the plan here is to first pick up the hook, use the hook to pull the small box closer, then drop the hook on the table, and then pick up the small box and finally place it on the large box. And so now motion planning is used to plan the geometric details, such as where to rest the hook, how close to pull the small box, and so on, to come up with a concrete trajectory. And in our approach, we actually build up this prior work from Marc Toussaint to solve this problem called logic geometric programming. And it combines PDDL planning with nonlinear trajectory optimization, but it does produce joint space trajectories like most TAMP algorithms. And these are only valid as long as the environment is static and perception and control are highly accurate. And if something changes, such as position of the small box, for example, then the joint configuration in the original plan is, for grasping that box is no longer valid. And so if we were to use this algorithm, we would basically need to stop, or the robot would need to stop and take like several minutes again. Okay, so what we propose here is to avoid having to stop and replan and choose to optimize over relative pose variables rather than joint space trajectories. So at the most basic level, a manipulation task can be reduced to controlling a point relative to a target frame. like controlling here the n effector relative to the box we want to pick up. So basically for the pick action, what we define here as a pose as a variable is the pose of the n effector relative to the box. And once the frame optimizer assigns a value to this variable, it can still be used no matter how the box moves, because the n effector will be controlled to maintain its pose relative to the moving box. And so similar for the place action, we also define a pose variable that is relative between the green box and the blue target box. And because of the relative pose, it doesn't really matter how the robot has actually picked up this green box. It only matters where the green box is relative to that target pose. And so that means really that these two actions are decoupled from each other, and that makes planning over the long horizon easier. And so this is the key contribution here. This is a TAM framework that optimizes trajectories over object-centric Cartesian frames rather than joint configuration, which requires a whole bunch of adaptations to the original framework that I'm not going to go in detail here. And so here's how this plan actually looks like that is produced. And you can see these objects are being perturbed. So they are kind of flying around because Toki is moving them around. And yet, because all the plan is defined relative to these objects, they still stay valid even though they change their absolute poses. Okay. And then, of course, it turns out that for some problems, optimizing over relative pose variables can be much quicker than optimizing over these joint configurations. So this Tower of Hanoi demo shows how relative pose variables allow to plan over really long horizons through the decoupling of the actions that this relative pose variable brings. You see that it's actually below half a second here that these two valid solutions actually get solved for. And then, of course, we also wanted to bring this to the real world. So here the poses of the objects are tracked just with the model-based trackers and some markers. But you see Toki here actually pushing around the objects, but also the robot, and yet the plan is still possible to actually execute. Okay, so just to summarize this work, this is the title of the work. Feel free to check out the paper or talk to Toki. And the main idea was to combine symbolic planning to create an action skeleton that is then translated into a constrained motion optimization problem. And it was specifically reformulated to optimize over relative Cartesian frames, which make basically the task and motion planning feasible in a dynamic environment. Okay, so that's interesting. So with this object-centric TAMP, we can now get around the computational cost of TAMP to apply it in dynamic and real-world environments. But it can, the initial plan still takes like sometimes minutes, but then, you know, when you actually execute it, it's adaptive to the poses. Okay, so if we now wanted to use a task planner actually in closed loop, we need a way to perceive the symbolic state of the environment, such as whether the blocks is, for example, in the hand or on the table, so we can pass this information to the task planner and replan potentially accordingly. And so this leads up to the next work I want to talk about that was actually presented here at ICRA, and it's called Grounding Predicates Through Action, which addresses the difficulty of learning symbolic state perception system. And so in computer vision, this is called visual relationship detection or theme graph generation. And I just have here 3 works that look at this problem from the computer vision community. And basically, the standard way or common approach to work on this problem is to collect a large database of images, have mechanical Turk workers automatically label whatever predicates they can think of, and then train neural networks to predict them from images. The problem is that manually labeling these predicates is expensive. So just one image like this one can contain a prohibitively long list of predicates that grows exponentially with the number of objects. And so these are actually all the labels that the mechanical Turk workers labeled, but it's not even exhaustive because here is a list of all the things that are still true, but we're not labeled. So really doing this exhaustive labeling would be infeasible. So in this work, we propose a much simpler way to obtain labels for training these kinds of predicates that we are interested in for robot manipulation. So rather than labeling predicates manually, like what has been done in the computer vision community and these previous works, our key idea is to label them automatically with symbolic actions. So symbolic actions as defined in PDDL contain pre and post conditions that describe basically how an action changes the symbolic state of the world. So for example, with this action, put an egg into the bowl, we know that before the action is performed, the egg has to be in the hand and the egg won't be in the bowl. And after the action is performed, the egg will be in the bowl and no longer in the hand. So just by knowing what action was performed in the video, we can automatically label the video frames with these 4 predicates. Okay, so how do we now do this whole thing of training predicate classifier? Basically, first we acquire a data set of actions. As a proof of concept, we use this 20 billion something data set, a large-scale data set of 200,000 videos of humans performing 174 common manipulation actions that we would love our robot to be able to do as well with all of these different objects. And so if we did like a back of the envelope computation, what it would, how expensive it would be to follow the standard approach of manually labeling all these predicates in these videos. And it would basically require 690 days of work for 200,000 videos to actually do that. And obviously that's too annoying and too expensive. So instead, we propose to automatically label predicates through actions. And what this still involves, though, is to define action, pre and post condition for each of these 174 different action classes. So if we're training predicate classifiers for a custom task planning application, though, this comes for free with the task planning domain. But 20 billion, this data set wasn't designed with task planning in mind. So we needed to, or Toki needed to define a pre and post condition for these 174 different actions. And for him, it took like about 4 days, basically, which is a huge difference, obviously, to the 690 days of work. And so now once you have this data and have done this automatic labeling, you can train this predicate classifier. So in just 4 days, we obtained an automatically labeled data set. Thank you to these people, well, to the data set collectors, obviously. But now we have this labels for the predicates that would otherwise have taken 690 days. Okay, so for the predicate network, we actually take an existing work, but here's how this looks like. You basically get as input a frame like this, and then you basically look at the bounding boxes of these objects that are detected there. And you want basically for these different input, 5 minutes, for these different input objects to basically predict the value of each of these different predicates. And so you want to do that for the cup, in this case, the hand, or also both of these two objects together, and even swapped around as well, right? And so this is how we want to use this network at test time. And so here's how we train that. We basically send a before and after image from this video of this action that we know is performed in this video into the network, along with the bounding boxes of the objects that we get from some object detector. And the network then outputs predictions for the before and after state, and we compare this prediction to the partial state labels obtained from the pre and post condition disjunctive normal forms. So we Toki derived an entire new loss function for this, basically based off the cross entropy loss between the predictions and labeled pre and post conditions to train this predicate network. And then we update the weights and train it to convergence. And so here are some examples of how this looks like on test videos. So this is closing the book, and you can see that the network correctly identifies the book as open at the beginning and closed at the end. Here's another example of poking the flashlight so that it falls over. And you can see that the network recognizes the transition from upright to not upright, and it also identifies when the flashlight and the hand are touching. And then, of course, we always like to actually show things on a real robot. And so we show how predicate classifiers can be used for closed loop task planning in the real world. And here we apply this predicate classifier that I just showed you directly to this robot environment. And we set up a task planning scenario where the goal is to clear the fruit off the table surface. And this is specified as this logical formula above. And you see that the task planner comes up with a sequence of action to satisfy this goal, given the current symbolic state. And the predicate classifiers predict the symbolic state in real time, so this is not sped up or anything. So the robot responds to failures that Toki is obviously inducing here to then replan immediately. Okay, so this work was here. The main idea was to exploit that actions change the symbolic state in a known way for cheap proposition labeling of video demonstrations. And there's basically an entire framework in that paper for obtaining these partial state labels for video demonstration and training these classifiers. And what is interesting is that you now have 37 different predicate classifiers that are relevant to really a lot of different actions, 174 actually. This should be 174 that can be then used for closed loop task planning. So the cool thing here is really that this was trained on real videos and not on some simulation task that you had to run with an actual robot. So this works directly on real images as well. And another thing in relation to scaling that I want to mention here is you see that these predicates, they are actually far fewer than the actual actions, but they are basically shared across all these different actions as well, which you could think of makes it easier to actually add new actions maybe to this domain that reuse these predicates as well and can then be used in this task planner, which is cool. So I'm actually out of time, so I won't be able to talk about this work called Concept of Robot, where we actually replace the hand design policies from this earlier task and motion planning work with learned policies. We basically used language and initial scene images input and then generated motion trajectories also for more than 70 different actions. So I'm not going to talk in detail about this one. I'm just going to show you maybe some outputs. This work we've done in simulation where we, again, actually also use this 20 billion something data set to use as a reward in training this one policy that generates basically that can generate action trajectories for all of these different example tasks that you see here. And because we use real language as input as well, we can also change it slightly, and yet the policy actually still outputs reasonable trajectories. So this was work that was done with Lin Xiao and also Toki as co-authors. And again, we learned in embedding the space there for what we call manipulation concepts that are indexed by natural language instructions. And there's a whole setup of an imitation learning framework where we use an activity classifier trained on this video data set to provide the reward. We get one policy that can execute 78 different tasks. Yeah, so with that, what we're currently working on is to actually connect basically these different works together and actually automatically sequence them. And here are some open questions that I want to close this talk with that we can maybe discuss, maybe in the panel even, or if you have questions about. So this scaling robot learning, I'm wondering scaling over what exactly? There are many different ways, but I'm thinking of it a lot of like, how can I avoid this complexity of maybe reinforcement learning from scratch? Because I do in the end want to make things run on a real robot, and that's just very difficult, especially for manipulation tasks, to do that well and over many different tasks, over many different objects. Also, I showed you two works, one that uses natural language instructions to actually index into a policy that generates these different tasks. And the other one actually used the task planner with a hand-defined domain. And so one of the questions that I would also find interesting is how do you bridge these two domains? Then another question where people, I think, have also different opinions is, should you use a symbolic planner, or would you actually want to learn how to sequence these actions as well? And I think there are also a lot of trade-offs here on complexity of learning as well. So with that, I thank you very much for your attention. This is my research group. We took this photo like a month ago or something like that for our first mini retreat since the pandemic. And so my funding sources would I think as well.